Okay, thank you very much for coming back in. I appreciate it. And why are we talking about noise? Speaking of noise, my voice projects. So we talk about noise as consumers, as customers, whether it's in automotive, whether it's in wind energy, pretty much any industry, noise is a topic of discussion. And just to prove that to you, I have this slide. So in automotive, this just shows you at idle in blue and at 70 miles per hour road speed in green, it shows you what the sound pressure level inside your vehicle would sound like in decibel of sound pressure level for 1,500 vehicles. So your vehicle probably is in that range somewhere. And obviously, depending on what kind of vehicle you have, whether it's a big vehicle that might experience a lot of surface area and therefore a lot of wind noise, or a sporty vehicle that might experience a lot of interaction with the road and therefore a lot of road noise. Whatever kind of vehicle you have, it's probably going to be in those ranges. And noise is often associated by the consumer with quality. And so to manufacturers, it's very important. And you notice it. And just to prove that to you, we're going to play a video right now. And this video is going to prove to you that noise is something that you can perceive at the levels that we talk about as engineers. This is a reference level. Hear that level. Could you hear that difference? You're not supposed to hear that difference. Reference level again. Could you hear that difference? Engineers get very ecstatic about 3 decibels of sound pressure level. Reference level again. You could definitely hear that level. 5 decibels, that would get you promoted in a noise and vibration group. Reference level again. And this makes you the technical fellow for noise and vibration in the company. So that basically, 10 decibels equates to a reduction by 1/2 of the actual sound pressure level amplitude. So again, the reason we're talking about noise is because it's something that's important to consumers. It's certainly very important to manufacturers too. Now, when is it important to manufacturers? Well, oftentimes it becomes very important to manufacturers at the end of the process, because you've made the vehicle, right, all the prototypes, you've gone through all the testing, and you get to just the moments before launch, and there's a noise issue, there's a vibration issue, there's an issue associated with the harshness, how it feels when you drive it. And what do? They use what they often call a bolt-on solution. It's a constrained layer damping treatment. Right? They have to put on other material to make the vehicle quieter. Or some other type, maybe a vibration absorber, right? To handle a particular narrowband source of vibration or noise. Whatever the solution, it typically comes at the end. Now, that is expensive because it's happening late in the program, and things that happen late in the program are often very, very costly. Now, the kinds of things that we want to try to talk about and encourage in composites are things that happen, you guessed it, earlier in the program. Solutions that tend to be more simulation-driven. Solutions where you've already kind of worked out some ideas around what type of dissipation you could glean from the material. What type of structural joints you could use to dissipate, for instance, structure-borne noise. And so these are all the types of things that in composites, certainly in IACMI, folks within IACMI are addressing. So one of the interesting challenges and therefore opportunities that in composites, like any new material innovation will face, for instance, in vehicle, is that we as passengers, as consumers, adapt to noise sources. So let's say there's a source of engine noise. Well, over the development of a vehicle platform, that source of engine noise is reduced. Okay, let's say there's a source of wind noise. Well, over the course of development of a vehicle platform, that source of wind noise is developed out of that program. And so on, and so on, and so on. Until what happens? Somebody notices the bushings. they noticed that the compounding, the chemical compounding that's being used for the bushings that basically isolates you from almost everything that's happening on the road that you don't want to feel, right, as a passenger. Somebody notices that the global sourcing that you're doing for the bushings varies due to the subtle variations in the chemical compounding processes, right? These are real challenges that the industry faces. And nobody ever noticed that before. Why? Because there were other sources of noise that were dominating the conversation. And those sources of variations drive not only issues in noise, but also vibration-related fatigue failures as well. So the idea here is that even if noise isn't the predominant issue when you start developing a new innovation to go in a vehicle, it will eventually be part of the conversation because it's part of that overall ecosystem for noise, vibration, and harshness. So, what are the kinds of solutions that suppliers and OEMs develop? One of IACMI's partners at 3M, for instance, use composite material innovations to develop solutions to handle a myriad of challenges. So, for instance, inside a compartment, in addition to addressing challenges in thermal insulation, you can also address acoustic insulation. Essentially, Thinsulate is a solution for doing both of those things in the same material, right? By looking at transmission loss across the material, developing a material that not only is a thermal insulator, but an acoustic insulator, if you will, damping out those acoustic waves that would otherwise travel through that door compartment area, you can achieve both of those solutions in the same material. And this, we think, is a real opportunity for composites because they're highly engineered materials. So again, stepping back to our goals in IACMI related to 25% lower carbon fiber reinforced polymer cost, 50% reduction in embodied energy, 80% recyclability. Do these goals relate to NVH? What are the relationships between these goals and NVH? So if you look at those goals, you see phrases like lower cost. You see phrases like reduction in energy. And if you think about the kind of conversation we were having earlier, you might save cost on material, but what if you have to add a constrained layer damping treat, a vibration absorber? What if you push the cost of noise solutions downstream by introducing material innovations for lightweighting? What if it becomes a zero-sum game in lightweighting? What if you take weight out, but you have to put weight back in to achieve the noise, vibration, and harshness performance? That is a real story that happens every single day in, for instance, the automotive industry and in other industries. So the idea here is to think about this at the beginning of the process through using simulation tools, through doing characterization of these new materials that you all are developing, and in leveraging what IACMI has available to help in any way it can to help develop useful products that can be adopted in this space and in other spaces. Now, I've been talking about automotive almost from the beginning, but I don't want to limit it to that. In fact, we have a workshop on Thursday, and I really appreciate, Uday and I really appreciate everybody that signed up for that. I think it's going to be a great workshop. And so Nextsight is helping us direct that, and I'm really looking forward to the conversation on Thursday morning around NVH and opportunities around composites. But turning from automotive, thinking about kind of the way in which IACMI works, leveraging across these product families, think about wind energy. Is noise a consideration in wind energy? So this is a really interesting, and I knew Derek would appreciate this, this is a really interesting paper I found as I searched and searched for just the right thing to include here. I always knew, for instance, that blade tip-speed ratio was an important factor in performance, Obviously, the faster the blade rotates relative to the mean wind speed, the more energy you capture in a wind turbine. That stands to reason. But of course, the faster the blade rotates, what else happens? The noisier, potentially, your wind turbine is. So it turns out that much of the design envelope for a wind turbine is around what? Is around noise. It's around noise setbacks. It's around this great chart that may be a little too small for you to read, but it's about 300 meters is about that setback distance from the turbine base to the nearest residence when you're thinking about a wind farm siting. And so setback requirements are really developed around noise requirements. So think about the kinds of composite solutions in nacelle, in wind turbine blade structure that you might think about enabling through the use of advanced composite materials in wind energy systems. So I mentioned this earlier, which was if we want to enable the kinds of goals that IACMI is after relative to lower cost, we have to think about kind of manufacturing over the entire timeline for manufacturing. And so if we think about lightweighting in general for automotive, you know, we can kind of boil it down to Newton's law. And I swear this is the only equation in this whole presentation. It's my favorite equation as a dynamicist. And of course, everybody knows it. You know, Bill is just eating this up, right? F is equal to ma, right? And so I didn't do a lot of algebra to get to the other side of that equation. I know everybody can follow that. So what does that equation say? That equation says that as I lower the mass, what happens? What does my material, what does my panel, what does my structural assembly, what does it want to do more of? It wants to move. It wants to be a better loudspeaker, right? It wants to convey more structure-borne noise and or vibration. That's just inherently what it wants to do. Those are the physics, as we say. So again, in thinking about lightweighting in composites, that's just like a physical law. However, composites have some really attractive features, right? Things like we can control aspects, for instance, the incorporation of foams, to look at aspects, for instance, like porosity and the use of that to do better sound attenuation in material. That's why there's a lot of foam in aerospace, because foam's really good at attenuating noise, for instance. So this is a physical law, but there are a lot of attractive solutions in composites that help us circumvent this type of challenge. And again, we want to avoid lowering the mass, just bulk mass of the material, just only to shift it downstream to a bolt-on solution at the very end of the program, which is costly and it's also annoying to manufacturers. So as an example of a really clever solution, again, I chose solutions, you'll see a theme. All these solutions are from our partners in the IACMI family, but it just turns out that our partners are great, and so they happen to have a lot of great material innovations in this space. So one of the quintessential noise and vibration challenges, which all of you have thought about, I guarantee at some point, and you've probably complained about it, is stick slip. And you probably didn't call it that when you went to the automotive dealer, but you probably said, my car is making this funny sound. It's making a squeak. It's making a rattle. And that's due to a stick slip phenomena, okay? And it's very hard to predict, very hard to simulate. So this solution that Dow Corning came up with focused on the development of anti-friction coatings. And it did this so that it could incorporate dissimilar materials in design of body structure, panel structure. And the idea here was to avoid doing what you have to do if you don't do this, which is incorporate more fasteners. Why do you incorporate fasteners? To avoid things like stick slip? Because there's no better way to dissipate energy for noise, vibration, and harshness concerns than to put a joint in your system. Joints are wonderful. They are a great way to dissipate energy, but they're also heavy, and they are another design feature. And so I love that talk earlier about joints. I would love to think about that joint with respect to noise, vibration, and harshness. So here, the idea was, well, just prevent the joint from being a source in the first place. And that's the solution that Dow Corning came up, again, by thinking about it as a material innovation. There is so much to learn from work that's gone on over actually the last 30 or 40 years. I've just chosen the last 16 because I did a short Google search just to kind of show you that's from 2000 to about 14,000 papers published on noise and vibration harshness, just to kind of show you like the volume of work that's going on in this field. So there's a lot of work that's going on in just general noise and vibration in automobiles and material solution for noise control in a range of fields, including like in aircraft cabins, in off-road machinery is a big user of this technology. I talk to anybody that operates a piece of off-road machinery and they'll tell you they'd like it better if it were quieter. And so attributes of composites that bring in NVH are also part of this literature search. And if you look at this literature, it's interesting. First of all, you can break it down in terms of noise and vibration. I mean, I don't find that particularly insightful. I mean, noise is taken off, vibration maybe is leveling off. I'm not sure you can say that from this data. But what I do find interesting is you look at the trends. If you look at what was happening like in the early 2000s, largely speaking, the work that was going on in NVH was very empirical. You did a lot of testing mostly. It was linear analysis. So in other words, all the analysis was FEA straight up linear, okay? And it was for the most part uncoupled. They didn't do a lot of full systems, like vehicle systems. They would do like body and white separate, right? From suspension separate from so on and so on and so on. But if you look at what's happening now, the simulations, right, are coupled and are highly nonlinear and are incorporating those phenomena like stick-slip phenomena, for instance, and the other complicated phenomena that really drive a lot of the unpredictability of noise, vibration, harshness. So there have been a lot of findings over that period of time that have enabled these kinds of solutions. So the other thing that's happened, of course, is there have been standards that have been put in place through all that testing, through the simulation, and of course, there's a lot of work out there on composites. That's what that little arrow is showing you. There's a lot of guidance for customers, from material suppliers to OEMs, and in between on guidance relative to composite materials. So I mentioned where is the lowest cost, maybe highest impact area relative to NVH development. Where could you maybe make the biggest dent? No pun intended. I guess in composites that's totally a useless analogy, but anyway, where could you have a big impact in composite material development for NVH? And it would be back at the beginning of a program in the simulation phase. And so here I'm just showing some work by Dassault Systems relative to looking at body and white and essentially looking and understanding resonant phenomena. And if you think about a vehicle from a standpoint of wind noise, road noise, engine noise, basically what you don't want to do is you don't want to excite resonance. We all inherently know that. And so what you're seeing here is using simulation buttressed with experimental validation as a means to develop predictable design and development strategies for composite structural assemblies. And the idea is so that you don't get to the end of the program and have to have those bolt-on solutions, so that you have a predictable spectrum associated with your noise or associated with your vibration characteristics. And again, one of I think probably the biggest challenge, I would say, for composites in NVH for automotive is that there's no one challenge, because you've got low frequency challenges like at idle associated with what your engine's doing, unless you drive an electric car, in which case I'm not talking to you, but you have challenges associated with what's happening at the low frequency end. You have challenges associated with what's happening at high frequency, mid frequency. They're all different. They're all different challenges. But again, that's where composites offer some real merits, because they provide what we call band gap solutions. You can develop the material in such a way that it almost acts as a filter, in those different frequency ranges, and you can literally design its material and geometrical characteristics so it serves as, again, a band gap in those areas. And so here what I'm showing you, for instance, is using sophisticated bonding techniques, joints essentially, adhesive joints, to do the type of thing that you need to do to achieve low frequency isolation from noise sources, but also acoustical foams to achieve attenuation at the high frequency range. That's typically how it works with these types of materials. And again, one of the other challenges in automotive is that you're not just developing something that's got to be quiet, it's also got to live inside of an engine compartment. So we heard earlier from our colleague at Volkswagen, and so I thought this example, again, through our partners at BASF and Volkswagen, partnering up to develop a very innovative solution for addressing engine noise at the source inside the engine compartment. And the big innovation here is that these materials, just like composites, their properties vary with temperature. And one of the properties that really impacts both vibration and noise performance is what's called the loss factor. It's basically the damping, the inherent dissipation in the material, and that property will vary significantly, mostly associated with the resin in the material, will vary significantly with the temperature. And so that's what really is the challenge to address here, and they developed a solution around that. And finally, I think this is among my last slides, if I turn to IACMI and kind of the model, you know, where else have they developed noise solutions and vibration solutions? And are there things we could learn from that? Well, yeah, there are. They've developed a lot of solutions in aerospace, in aircraft, because they deal with wind noise. They deal with, at very high speed, they deal with engine noise, right? They don't deal with ground noise as much, but you know, tire road interaction, but they deal with it a little bit. And so the point is, we have partners across that whole spectrum, from the aerospace, from the automotive, you know, from the wind energy. And so the idea of bringing all those together with material suppliers to develop solutions that cut across those sectors, I think is a great opportunity for IACMI. So, you know, really our question today and Thursday is going to be, you know, what do you think of this strategy of trying to support industry around NVH for composites at the beginning as opposed to the end to help encourage adoption by incorporating NVH to get more market pull for composites in these project proposals, avoid shifting cost to the late stages of program development by doing more simulation modeling, doing more characterization of materials. Wouldn't it be great to have a library of material characteristics around composite noise, vibration, harshness? That doesn't exist. It doesn't exist for bushings, actually. And so I know that because I've done projects on that with sponsors. So leverage unique supply chain and vertically integrated partnerships in place, again, to achieve this zero-sum game. The great thing about IACMI working across in a vertically integrated manner is we don't have to work on one thing at a time because we have the potential to work across these teams. And I think that's what's going to be required to avoid this zero-sum game, which often is what innovators face in this space. So that's what I have. And I have the benefit and privilege of getting to introduce the next speaker. I was told I could go over 5 minutes because we brought you all in late so that you could hear this riveting talk. That was a joke. So I'm an engineer, so I have to tell you where all the jokes are. So I don't know, Robin, should I go ahead and introduce Lenny, or should I take a question? What do you think? Q&A. Are there any questions that I can answer? Yeah, Steve.
What do you think about active techniques, noise canceling systems and the like, as a solution to our problem?
Yeah, so the question is, Steve's asking active noise control, active vibration control. You know, I mean, active suspensions are a form of, you know, whether they're air ride or magnetorheological fluid damper systems, those are all a form of what you're saying. Those are certainly here to stay. I'm aware of active noise control solutions, not around noise perceived by people that live around wind turbines, but around other dimensions of wind energy in terms of environmental impacts and the like. And so, you know, I think generally speaking, it goes like this. If you have a very broadband issue, active control, is almost what you got to do. If you've got something really narrowband in frequency that's very targeted, you can live with passive means. Or if you can like isolate it to a couple different ranges, you can implement kind of piecemeal passive solutions. Broadly speaking, that's usually how it works. So usually what you're trying to address drives you to kind of a solution. Does that make sense? Yeah.
Has anybody used the foam as a scaffold? Bring in like high loss materials and use it like as a filter then to take out what you want?
Yeah, so the question is, has anybody used foams as a
Scaffold as a housing.
absolutely, as a means to bring in? So there has been quite a bit of work done by 3M and many other material suppliers and innovators. And so a lot of that work's been in that I'm aware of has been in aerospace. And again, the idea of having foam materials, cellular materials, is that you can just imagine the noise gets trapped. It's like a mousetrap, right? It gets trapped and it can't get out. So because of that, it experiences a lot of internal reflections, and therefore it's a very dissipative media for things like noise. So I think foam is definitely a piece of the overall solution, and certainly it's something that is being looked at and has been looked at. Yeah. Yeah, Cliff.
Doug, could you speak to the differences in what is predicted and observed in component versus system?
Yeah, so the question is, could I speak to the differences between what's observed in a component and what's observed in a system? So I think, again, just kind of giving you the same broad answer I gave Steve a second ago, I think, if you think about a system, you've got all those sources coming at you. You've got engine, you think about the car for a minute. You got the engine, you got the road, you got the wind. And they're all coming at you from different angles, right? It's like a multi-input, multi-output problem. So from a standpoint of what's predictable, the kind of work I talked about where you look at system resonances, right? How is the system going to respond regardless of which excitation we're talking about? Those kinds of things are readily predictable. Now, what's not as predictable? Well, what's going to be the actual amplitude of response? Why? Because damping is a really hard thing to predict, like using first principles. You have to measure it. You have to have somebody who's produced a database of damping information, like IACMI, for instance. And so that's a difficult thing to predict. Forced response is difficult to predict because you need the damping information to get actually what's happening, right, at that resonance. At the component level, I think what you typically focus on is, you're assuming what the system is doing to the component. And so you're making a big assumption, but you can kind of get a general sense of what your envelope is based on that. And so you can get really good definition around material properties, geometry, et cetera, but you've made the assumption of what's coming in. So really you almost have to couple the two to know what the excitation is and how your system will respond, because it's a system at the end of the day. I don't know if that answers your question. Okay, I probably went way over my time. Go ahead, please. Yeah.
What are your thoughts on structural solutions in NVH and its feedback into crashworthiness?
Structural solutions in NVH and feedback into crashworthiness.
Yeah.
Wow. I'm going to have a drink and then answer that question. I don't drink. That's why that's funny. So I will say this. I mean, one of the interesting things to me about composites in general is sort of the energy absorption capacity of composites related to the connectedness of the material, right? All of those joints and interfaces. All right? So from a crashworthiness standpoint, joints and interfaces being pertinent to understanding energy absorption. Those joints and interfaces are also very pertinent to understanding how materials dissipate energy, whether it's vibration or noise related, right? Structure-borne, airborne, whatever. So I think that is a common link I see. It's one link. It's not the only one. We'd have to go ponder that question, but that's a thought I have. Interfaces are really, really important. So somebody like Larry thinking about joining and techniques, you know, he could really, I think, wrap his mind around that question and go deeper. Okay. Well, thank you, everybody, very much.